All right, let's get started again. First thing I want to do is quick recap of the big idea from last time. So last time you kind of got a bunch of vocabulary just dumped on you, kept talking about interpretations, sentential interpretations, atomic sentential interpretations, tautologies, and we did some things with truth tables. So I want to re-walk you through big picture what the author was trying to make an argument for. So the whole focus of the chapter so far has been on identifying when we have a valid rule of logic and identifying when we have an invalid rule of logic. That's been the focus so far. And then we did a couple examples of some proofs using rules of logic. So how do we know when we have a valid rule of logic? We have a valid rule of logic if that rule is a tautological implication. It's an implication that's always true. Alpha implies beta is a valid rule of logic if it is always true. It's a tautology, always true. An example of a valid rule of logic, here's one. This implies this. This is a tautology. It is always true. So not every implication is a tautology. Special implications, it turns out, are going to be tautologies. So when do we have a valid rule of logic? When we have a tautological implication. What does it mean for something to be a tautological implication? It means that every sentential interpretation of it is true. Regardless of how I replace its sentences, as long as I replace the sentences in all occurrences. So if I did an interpretation of this, I'd have to replace both those P's with the same sentence and both those Q's with the same sentence. As long as I do that, it should be true. So we have a tautological implication if every sentential interpretation is true. Every sentential interpretation is true if every atomic sentential interpretation is true. What's an atomic sentential interpretation? It's where we replace the atomic sentences with just atomic sentences. We don't add more structure. And now, every atomic interpretation is true if the truth table for it is always true. That's what we do with the truth table. We test all the atomic interpretations. Because when I have something that I'm testing, is this a rule of logic? I'm testing, I can replace P with either a true statement or a false statement. Doesn't matter which atomic sentence I replace it with, but that atomic sentence is going to be something that's either just true or just false. And so you test all the possible ways that you can substitute those with trues and falses. And that's what you're doing with the truth table. So what's the big idea there? It's if you can construct a truth table for something that's always true, then it's a valid rule of logic. So scribble out one. We'll kind of jump ahead. We'll look at this for a second, just to use it as an example, and then I'll come back and fix this. So here is going to be a valid rule of logic. This implies this is a valid rule of logic. How do we test that it's a valid rule of logic? We build out the truth table for it and see if the truth table is always true. So let's build out this truth table really quick. Notice that this only has two atomic sentences showing up in it, alpha and beta. So there's only four things I could do. In all my atomic interpretations of the sentence, that means I have to replace alpha with an atomic sentence, and I have to replace beta with an atomic sentence in all occurrences. Every atomic sentence is just either true or false. So I can replace alpha with a true one and beta with a true one. That's what we're handling in this case. I can replace alpha with a true one and beta with a false one. That's what we're handling in this case. I can replace beta with a false one, or alpha with a false one and beta with a true one. And that's what we're handling in this case. And then finally, I can replace them both with false sentences. In other words, I can replace alpha with the sentence, 2 plus 2 is 4, and beta with the sentence, the sky is blue. That's a true interpretation, where I'm plugging a true there. I can also replace it with the true sentence, that 9 is greater than 6, and 4 minus 5 equals negative 1. There's an infinite number of atomic interpretations I can make for this sentence, but all those atomic interpretations, I'm doing one of four things. I'm making alpha true and beta true, or alpha true and beta false, or alpha false and beta true, or alpha false and beta false. So that's what a truth table is testing. It's all the atomic interpretations. So if the truth table is always true, then every atomic interpretation is true, then every interpretation is true, then it's a tautological implication, then it's a valid rule of logic. So if you can make a truth table for it and it's always true, then it's a valid rule of logic, was the big picture idea that the author was trying to get across. And so this is the mechanism by which we can test it. So let's run through and see that this is in fact a valid rule of logic. Let's see if alpha is true, not alpha is. False. Again, false. Not false is.
True.
And not false is. Sorry, sloppy true. Alpha implies beta. We'll have more to say about this in a second, but for now, we remember that true implies true is. True. True implies false is. False. False implies true is.
True.
And false implies false is.
True.
Now over here, we're doing not alpha or beta. So we're ORing these two together. True or false is.
True.
False or false is.
False.
True or true is.
True.
Sorry, false. And then
False or true?
false or true, sorry.
It's true.
Lost track of what I was looking at. Okay, now we're doing this column implies this column. True implies true is.
True.
False implies false is. True implies true is. True implies true is. And so under every sentential interpretation, or sorry, under every sentential atomic interpretation, this is always true. Which means, it is a valid rule of logic. And so if you know that alpha implies beta, then you know alpha is false or beta is true.
So what does sentential atomic interpretation mean?
So a sentential interpretation is I can replace the sentences with any sentences. A sentential atomic interpretation is I can replace the atomic sentences with only other atomic sentences.
Atomic meaning what?
An atomic sentence it's like an atom sentence. It cannot be divided up anymore. The definition of an atomic sentence is a sentence with no sentential connectives.
You can't remove anything from it to change the value or the meaning. Is that what you mean?
Yeah, it cannot be reduced anymore. Now there's a technicality there. You can't mess with the terms.
Right. So what you're saying is I can't throw out any random statement and go through this process and create a rule of logic.
Yes, not every statement is going to magically give you a rule of logic.
It has to be an
The vast majority of them, not that, it has to be atomic. So let me give you an interpretation. So I tell you, if it's cold today, then I won the lottery. There's a sentence. I may give you a sentential interpretation of that now. I say, if it's hot today and it's raining and I saw a butterfly, then I won the lottery or I went home. I added a ton of structure to that. I replaced my first sentence with the conjunction of three sentences, and I replaced my last sentence with the disjunction. But since it's still a sentence implies a sentence, it's an interpretation. I didn't change the overall structure. I added substructure.
Okay.
So that is not an atomic interpretation.
That's just a regular.
So alpha implies beta, here's some sentence. I replace it with some other sentence, A implies B. Where A is just a different sentence than alpha, and B is just a different sentence from beta. That was an atomic interpretation, assuming that those were atomic sentences and those were atomic sentences. I could have also replaced alpha with A and B implies C or D. Now this is an interpretation of this, but it's not an atomic interpretation, because I've added substructure.
Gotcha.
So the overall structure always has to be there in every interpretation. It's just that when you're doing an atomic interpretation, you didn't add any substructure.
Okay.
When you do an interpretation in general, you may or may not have added substructure. But you can never change the overall structure, or it's not a sentential interpretation.
It's not a tautology.
Well, so a tautology is something that's true under every sentential interpretation. Pick this. Replace P and Q with any sentence of your choosing. Get as wild as you want. It will always be true.
And what if they're not sentential connectives? What if they're not? What if they are this big mess that you just talked about?
You could pick P to be the biggest, ugliest sentence you could think of, and you could pick Q to be the biggest, ugliest sentence you could think of. And you plug it all in. And if you plug it into this form and you work out that big, hideous truth table, you're going to see that what you're left with is true, 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 all the way down.
Okay, I see what you're saying.
So as long as you maintain this overall structure, any substructure you add is completely irrelevant. It's still going to be always true.
Okay.
So with all that, let me walk through the thinking one more time. If the truth table is always true, that means that every atomic interpretation of it is true. If every atomic interpretation of it is true, then every interpretation of it is true. And if every interpretation of it is true, then it's a tautological implication. If it's a tautological implication, it's a valid rule of logic. So all these are going to be valid rules of logic. That's the overall thinking. So in short, we have a test. Is something a valid rule of logic? If you can make a truth table for it and it's always true, yes, it's a valid rule of logic. Here is not a valid rule of logic. Alpha implies beta, that's not a valid rule of logic. Not always true. Okay. Now, we also have a test for if it's an invalid rule of logic. When is it an invalid rule of logic? Any interpretation that makes the premises true and the conclusion false. If there is a single interpretation that makes the premises true and the conclusion false, then that rule is invalid. We often call this a proof by counterexample. If you can find a counterexample to the rule doesn't hold. And so you can reject the rule. Or, that's equivalent to, the truth table is not always true. Well, I shouldn't say it's equivalent to. But if there's one false shows up in the truth table, then that means that there is some case out there that makes it false. How do I know alpha implies beta is not a valid rule of logic? Because there is some case out there that makes it false. Namely, when alpha is true and beta is false. Then this is false, so it cannot be a rule of logic. There are some conditions under which I can make it false.
So when you say the premises are true and the conclusion is false, are you saying both alpha and beta are true, but whatever the rule is?
The left-hand side is true, but the right-hand side is false.
Oh, so you're talking about implications.
Yes.
Okay.
So it's always going to be, all our rules of logic, with the exception of two, are going to be implications.
Okay.
The two exceptions are going to be the law of excluded middle and the law of contradiction. Outside of that, all our rules of logic, all our rules of logic are going to be implications. So, if the truth table is not always true, then that means that there is some counterexample out there, which means it is an invalid rule of logic. Okay. Got a little subtlety that's worth noting. So, if I tell you I have some rule of logic, and I tell you it's for sure a valid rule of logic, what do you know?
The truth table is always true.
You can construct a truth table for it that's always true, right? And the answer is no. Subtlety here. If you can construct a truth table for it that's always true, then it's a valid rule of logic. Just because it's a valid rule of logic does not mean that you can create a truth table for it that's always true. And I'll give you an example. Here's a valid rule of logic that you can construct a truth table for. Here's another valid rule of logic that you can't construct a truth table for. We will prove that this is valid in logic. If A equals B, then A plus C equals B plus C. There is no truth table for that. How on earth would you construct a truth table for that? Plug in all the possible values for every number you can think of. So if you can construct a truth table, that's always true, then it's a valid rule of logic. But just because it's a valid rule of logic does not mean that there's some truth table in existence you can use to prove it. So we can't only rely on truth tables. Truth tables are one way for us to discover valid rules of logic, and they're the ways that we discover our simplest valid rules of logic. We also have to rely on derivations. We will not prove this to be the case with the truth table. We will prove it with a derivation like what we ended last class with. So truth tables are nice. They're good for handling the simple pieces, but in the long run, we need derivations. We have to have derivations. So, for finding rules of logic, valid rules of logic, there's two ways we can do it. One way is just a truth table. The other way is a derivation. Now, truth tables are nice. Why are truth tables nice? You always know how to calculate the next value. You could just mindlessly fill out the table and ultimately prove what it is you're trying to prove. That's one thing we like about truth tables. That's what's tough about derivations. There is no rule for here's the next step you should take. And you just have to figure it out. That's why proving is hard. You just have to make the connection and see where to go next. So truth tables are nice because you always know what to do next. Whereas with derivations, there is no guarantee on what you can do next. Truth tables, on the other hand, can become very tedious. If I've got some expression that depends upon 10 atomic sentences, you would have to fill out a truth table with 1,024 rows. If it had 30 atomic sentences, you would have to fill out a truth table that had well over 1 billion rows. So derivation can save us a lot of the work that truth tables would require us to do. And on top of that, derivations can prove things that can't be done with truth tables, like this. Make sense?
Yeah.
So we're going to be, obviously the majority of the class is focusing on how to construct derivations, not truth tables. We've almost done everything we're going to do with truth tables. It's just what you start with. That make sense so far?
Yeah.
Okay. Now, has a request to re-go over vacuously true. What does it mean for an implication to be vacuously true? An implication is vacuously true if it is impossible to satisfy the antecedent. Now, we use examples from our universe all the time as examples of vacuously true sentences, which causes our intuition to apply all the rules of physics to the scenario as premises to determine that a sentence isn't actually vacuously true. What do I mean by that? There's a huge difference between statements of the form if then and statements of the form if it was the case, then it would be the case, ... Let me give you an example. Here's a statement that's true. If there are 10 people in this room, I'm a purple dragon. That is true. It is impossible to satisfy the antecedent there are 10 people in this room. That's impossible. On the other hand, if I were to say, if it was the case that there were 10 people in this room, then it would also be the case that I'm a purple dragon. That is not a vacuously true statement. Because now, this is introducing time into the equation. It's allowing us to change the scenario. And so it is no longer impossible to satisfy the antecedent. It is very possible for me to get 10 people in here. It is impossible right at this instant for there to be 10 people. So huge difference between if then versus if it was the case, then it would be the case. When we're doing logic, we don't have any notion of physics. We don't even have a notion of calculus. We don't even have a notion of set theory. So you can't introduce thinking what you could physically do in this universe to try and say that's a dumb definition in logic. So that's one thing to keep in mind, is if then is very different from if it was the case in our universe that then it would also be the case in our universe that Those are very different. Now, here's the unsatisfactory answer, but the best answer. Why is it that false implies true is true? Or why is it that false implies anything is true? It's by definition, which is very unsatisfying. So, why is it that false implies false is true? Because that's the way we define that symbol. We define that symbol, so if you put a false there, arrow, false there, then it's true. Remember that logic doesn't care about English. The word implies is the English word we attach to this meaning right here. So this is exactly what it means. And then we use the English word implies to help capture our intuition. So it's an unsatisfactory answer, but by definition, that's what it is. Now, ideally, we want to connect our intuition with what it is, but it's this by definition. That's just a definition of implies, period. And so the English word implies is the best thing we can think of that helps attach what we're getting at with those symbols. Now, here's one other way that I've noticed helps people with vacuously true statements. And that is to think about not alpha or beta. So alpha implies beta says the same thing as not alpha or beta. I tell you, if I'm wearing shoes, then I'm wearing socks, says the same thing as I'm not wearing socks or I am wearing shoes. If I'm wearing shoes, I'm wearing socks, tells you either I'm not wearing socks or I am wearing shoes. One of those has to be true, right? So if you can make this connection in your intuition, then a truth table can show you that these two are actually logically equivalent to each other. This is true when this is true. This is false when this is false. True, 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 true. So they're logically equivalent. So if this connects in your intuition, not alpha or beta, it says the same thing as alpha implies beta. If you can get that to connect in your intuition, then hopefully that helps connect why vacuously true statements have to be true. When I say, if there's fire, then there's oxygen, says the same thing as there's not fire or there is oxygen. They'll say the same thing. And when is there's not fire or there is oxygen true? It's true in both these cases, when there's not fire. So implications have to be true in both those cases, which are vacuously true cases. Now there's one more way to connect it to your intuition. And there's a reason that this is the way we chose to define it. And it's because if you put me in some system, like algebra, some mathematical system, and you give me one false statement, I can now prove anything you want. And so that's why false implies anything is true, because with one false statement, I can prove anything. The example we gave is, if 1 equals 0, then I'm the Pope. And what was the thinking behind that? If 1 equals 0, add 1 to both sides, I now know 2 equals 1. The Pope and I are 2, therefore the Pope and I are 1, therefore I'm the Pope. And I can prove this with any absurdity you want. If you allow 1 to equal 0, or you allow 9 to equal 5. I can also prove true statements with this if you want. If 1 equals 0, I can prove 2 plus 2 is 4. 1 equals 0, multiply both sides by 0, we get 0 equals 0. Add 4 to both sides, 4 equals 4. And 4 is the same as 2 plus 2. And so 2 plus 2 equals 4. So I can prove any true statement you want, and I can prove any false statement you want, if you allow me a false antecedent. So that's another argument for accepting false implies anything as true. Because if you're in some concrete system, then there's probably a way to work out that derivation. So that's the third reason that vacuously true statements are vacuously true. Any more conversations about vacuously true? I know Parley's not here, and he always wants more of this.
It's just the structure of implies. Right. It's just the way that implies, it's just, that's the way it's defined. It's just,
so it is what it is by definition, but now there's a reason that that was chosen as a definition.
Mm-hmm. And where could we go to where that was derived and why it was defined that way? What could we?
I just gave you.
That? Who defined it that way?
Who defined it that way? That's like asking who decided that plus is defined that way.
But isn't there an answer to that? Was Aristotle who was?
Aristotle used it this way. Okay. Aristotle's logic isn't this granular.
Okay.
And so he wasn't using truth tables. He was essentially using set theory to argue his conclusions. So I can't give you, here's the guy who said that this is the way it's going to be, but it's the way that this notion in logic is used ubiquitously.
Right.
Anything else? Okay, so we have our truth tables, and we know how to use our truth tables to find valid rules of logic. We don't just want to use truth tables, we want to also be able to use derivations. And so now we need our rules of derivation, our rules of deductive reasoning. These are our start here. These 3 rules that we have listed out here are our rules of proof, our rules of derivation. Our rules of derivation are not rules of logic. One of our rules of derivation tells us we can use rules of logic. Okay. So rules of logic are presupposed in derivations. And they're in some sense more fundamental. Make sense? Okay. So, let's really quick recap what our 3 rules were. So we had rule P. Rule P was that we may introduce a premise at any point in our derivation. You can have all the premises you want. Because ultimately what you're proving is that some set of premises entail some conclusion. So you can start with whatever premises you want. You just have to make sure that the conclusion follows from those premises. Rule T, this was our one that says we can use rules of logic. Rule T says we may introduce S, some sentence, some formula S, into our derivation, provided S is tautologically implied by previous lines. So if one of my lines is alpha, and one of my lines is alpha implies beta, I can combine those together and conclude beta. If I know alpha is true, and I know alpha implies beta, I know beta is true. That would be using this rule. This is kind of the heart of derivation, is that rule. Making all these little logical connections step by step in your derivation. And then finally, we have rule CP for conditional proof, or conditional premise. No, I'm not sure which one it is. One of the two. What does rule CP say? It says, if we can derive S from R and a set of premises, then we can derive S implies R implies S, right? We're deriving S from R. So R is helping us conclude S. So if we can derive S from R and some set of premises, then we may derive R implies S from the premises alone. And this is one of the ways that we remove premises. So we put premises in there conditionally, and eventually we remove them. This you do all the time in your math without even thinking about it. Your teacher says, I want you to show that if 2x equals 4, then 5x equals 10. It is not the case that 2x equals 4. You say, let 2x equal 4. You put that there as a conditional premise. And you show, then 5x equals 10. What did you show? You showed if this is true, then this is true. We don't go around in math saying 2x is equal to 4, guys. That's what it is. That's something that you offer as a condition in your proof. Then you come to that conclusion. And what have you shown when it's all said and done? You showed if this is true, then this is true. We don't go around still saying this is true. That's what we're doing here. So if I can show that this follows from this, and all the other premises that we have in mathematics, then I can say that this implies this follows from the rules of mathematics alone. And this doesn't need to be a new rule of mathematics, that 2x equals 4. So you do that left and right. Every time you're writing a proof, and you say let, or assume, I should say, assume, da 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 da. Okay, so that's rule CP. Now, do some of the examples from last time. We'll scribble them over here. Hopefully I can get my camera so I get all of that and all the rules. I didn't check to see if that was possible. I think we're good. Beautiful. Okay. So, that was just me scribbling out the symbolization of what we did. But let me read example 2 again. So, example 2, what did it say? It said, if the Cards are third, then if the Dodgers are second, the Braves will be fourth. Either the Giants will not be first, or the Cards will be third. In fact, the Dodgers will be second. Therefore, if the Giants are first, then the Braves will be fourth. So that was the example. This is how we symbolized it. So I'm going to read it and re-symbolize it again. That's just to make sure I don't make a mistake. So 1. The first sentence was, if the Cards are third, so if the Cards are third, then what? If the Cards are third, then if the Dodgers are second, the Braves will be fourth. So then, if the Dodgers are second, the Braves will be fourth. That was the first line of our example, first sentence. This we are introducing as a premise in our derivation, and it only depends upon itself for its validity. 2. The second sentence was, either the Giants will not be first, or the Cards will be third. So, not Giants or Cards. We introduce that as a premise. It only depends upon itself, line 2, for its validity, or premise 2. What was our third sentence? Our third sentence was, in fact, the Dodgers will be second. So we were using D to represent the sentence, the Dodgers will be second. So in fact, the Dodgers will be second. That's a premise. It is only dependent upon line 3 for its validity. Therefore, if the Giants are first, then the Braves will be fourth. Therefore, if the Giants are first, the Braves will be fourth. So we're trying to prove G implies B. Maybe scribble that down here in our bottom corner. G implies B is what we're trying to prove.
Do none of the like numbers or it'll be like first, second, whatever. Does none of that count? Only right.
Because it keeps using the same sentence over and over again.
Okay, so you got to make sure that it's the same sentence though when you go.
Yes. So every time he said the Giants, he said the Giants will be third or whatever it was.
Right.
So he kept using that same sentence. We will learn next week how to break down sentences. Because right now, yeah, we are taking a sentence like the Braves will be fourth and representing it with just a big old B. We can definitely break it down, and there's more structure in what's being said there. That will be next week. So for now, we're taking these core sentences and working with them. But, so what are we trying to show? We're trying to show if this is true, and this is true, and this is true, then this is true. Now we could do this with the big ugly truth table. I could do the truth table that says C implies D implies B and not G or C and D all together implies the conclusion we're after, G implies B. And I could write out that truth table and work it out. And if this is a valid rule of logic, or in other words, if this does follow from these premises, this will always be true. But who on earth wants to work through that monstrosity? And so we're going to use derivation rather than a truth table. But looking for G implies B. Sorry, shouldn't have replaced what we're after. So, not D, B. All right. So this is what we're trying to prove. These are our starting premises. And we can use our rules of logic as we go. I'll say more about these when we get to them, but this is just redoing something we've already done. Okay. So, let's see what we can do now. So here's my given information. What can I conclude so far?
You can conclude.
Just really quick, make sure I didn't make any mistakes here.
C implies B. Oh no.
Not G or C. So you're gonna assume that G.
Not G or C is true.
No, you gotta assume that.
I know that G is false or C is true. That's what this is telling me.
No,
Right.
what I'm saying is you gotta say that if G is true, then C is false.
So, what are we trying to prove?
That G implies B.
Okay. So we're trying to prove an implication.
You assume the antecedent shall have positive.
There we go. How do you prove
Yes,
any
yes, that's what I
implication?
was- yeah.
Oh, is that what you're trying to say?
That's what I was trying to say, but I.
So introduce G now as a premise. A premise that we promise we're going to get rid of. So it's like I said, here's the axioms of arithmetic. Now I want you to prove that if 2x equals 4, 5x equals 10. So here I'm saying assume 2x equals 4, or something to that effect. Similar thinking. So I'm introducing G, I'm introducing it as a premise. We indent it to remind ourselves, I promise I'm going to get rid of this down the road. So that's my promise to you, is that when it's all said and done, we better not depend upon 4 for our validity. When it's all said and done, we better only depend on these 3 premises for our validity, or we've cheated. Because what we're being asked to do is to show that horrendous thing that I showed you at the start. That these 3 things imply this. Not that this somehow implies that. So I have to get rid of this as a premise, or I can't have it ultimately rely on this premise when it's all said and done. CP is our rule for getting rid of premises. So that's ultimately what I'm going to do to get rid of the premise. Okay, so now we're at line 5, and now what can we conclude?
Not C.
Not C. I know G is false or C is true. Is G false?
Not true.
So if G is not false, then C has to be
False.
true.
Ooh, oh my gosh.
If not, yeah, okay, sure. C's
Yeah.
Okay, you see it? Okay.
That happened the
G
same.
is false or C is true?
That
Is
happened
G
the
false?
last week too.
No, so C is true. It has to be one of those 2 things. We have that or that. We don't have that, so we have to have that. Okay.
Yeah, okay.
So, this, together with this, tells us what?
C is true.
C. So I know C, and this is tautologically implied by lines
2 and 3.
2 and 3.
2 and 4.
2 and 4.
2 and 4.
Right, so now we're using 4, but we can't use 4, right?
No.
By the end.
So
And
when it's all said and done, 4 better not be over here, where we've cheated.
Okay.
So far that's what we have. And just in case you're wondering, what is the rule we use in combining these 2? The rule we use, we're going to list out a bunch of our rules here. It's one of them. It's going to be this one.
Not B and Q or Q plus.
If I know P or Q and not P, then I know Q.
Right.
If I know one of those has to be true and that one's false, then that one has to be true. So I know that or that has to be true. That's false, so that has to be true.
Yeah. It's making sense.
All these rules have names. You can reference the names if you want. I'm never going to do that. I think it's a waste of time to memorize those names. You can just see the connection and say, it's just logic. Okay, so now we have C. What can we conclude?
That
D
D
implies
implies B is
D
true.
implies B, perfect. So we now know D implies B. This was tautologically implied by lines 1 and 5. 1 and 5. And there's some rule over here that says if you know P and you know P implies Q, then you know Q. So I know P and I know P implies Q, therefore I know Q. It's one of my rules over there. Okay, and now we are dependent upon 1, 2, and 4, right? For our validity.
And 5.
And 5.
These are the premises we're dependent upon,
Oh.
not the lines we come from. So 1 here means the premise introduced on line 1. 2 means the premise introduced on line 2. Good. So these are just tracking our premises, not the lines that we came from. Our lines that we came from will be tracked over here.
Oh, gotcha. Okay.
Good. Sorry, I should specify that there. Okay, now I know D implies B. What do I know?
B is true.
How do I know B is true?
Because D is true.
I know D, and I know D implies B. So these two together give me B. And so that was tautologically implied by lines 3 and 6, and I am now dependent upon premises 1, 2, 3, and 4. Okay, now what does rule CP say? It says if from our premises and from some new statement, G, we can conclude B, then we can conclude that G implies B without using this premise now.
Okay.
This is using rule CP, and we were doing it from lines 4 to 7. Lines 4 through 7, and we are now only dependent upon premises 1, 2, and 3. We are no longer assuming G is true. What we showed is if these are true, and if G is true, then B is true. So if these are true, then if G is true, B is true. That's what we showed.
So, okay. I see it.
It's like when you're doing arithmetic. What did you show? You showed if the axioms of arithmetic are true, then if x equals 2, then 2x equals 4.
Yeah.
And you get rid of your assumption that x actually equals 2.
Interesting.
And you get rid of your conclusion that 2x actually equals 4. All you're really saying is that if x equals 2, then 2x equals 4.
Yes.
So when it's all said and done, we just showed an implication is true. We didn't show the antecedent is true, and we didn't show the conclusion is true. We showed our premises tell us that if the antecedent was true, then the conclusion would be true. That's what we showed.
Okay.
There we go. And we're done. It's proven. Full-fledged proof. All the nitty-gritty detail. Good? Let's do our next example. So our next example, example 3 here, have it written to the side. I don't remember what all the words were for it. Do you guys care what the paragraph says?
Not really.
Okay, so one was somehow A implies B or C. So that was going to be introduced by rule P, and it is only dependent upon itself for its validity. Our next premise is going to be B implies
not A.
Thank you. B implies not A. That's a premise, and it's only dependent upon itself for its validity. What's next?
D implies not C.
You're trying to prove that A implies not B.
That's the end of it. A implies what?
Not D.
Okay, so here's what we're trying to prove. Here's our premises.
Okay, so we're going to assume A as our C.
Wonderful starting point. Anytime you're trying to prove an implication, assume the antecedent.
Is that every time, or can we ever prove an implication without assuming an
No, you don't have to. It's just good standard procedure.
It seems like
I feel like
proving by
doing
way of
that.
contradiction is the most standard that I've seen.
Really?
Proof by way of contradiction is what I've seen the most in the geometry textbook.
Proof by way of contradiction is using a similar mentality. It's saying, let's assume the opposite of what we're talking about as a conditional premise, and show that leads to contradiction. Therefore, our other premise is in fact true.
If
So
we
it would
know-
be assuming not A.
Kind of. We'll do reductio ad absurdum. That's going to be our fourth rule. So we've got our 3 rules so far. We're going to have a new rule called reductio ad absurdum, which will be indirect proof or proof by contradiction.
If If we don't have to assume our antecedent to apply our conclusion, then why do we do it?
Because it's easier to work with. Otherwise, you somehow got to work with these things as a whole to get that to somehow come out of it. You can do it, but it's just going to be ugly. In this case, it would be ugly. There's other cases where it could be simpler. You might remember back to your geometry test, I said, show that, what was it? If two things aren't equal, then they're not congruent.
I think so.
Something like that. And all you have to do is realize it's a contrapositive of something given. And so you didn't need to say assume and then show it, because you could work with the implication directly. You can say, I already know this implication, and this is just a reordering of that implication, so I'm done. So you can work with the implication directly, but it's harder as a general rule. So assume the antecedent. We got a new premise here, premise 4. We better have that gone by the time this is all said and done. Okay, so now I know A. Now what can I conclude?
B or C.
B or C from here. This is tautologically implied by
1 and 4.
1 and 4. And so we're dependent on premises 1 and 4. Okay, so we got that. What else can we conclude?
B implies not A, so
Oh, it's B, B or C right there.
well we have
Oh, A is true, so B has to be true. No?
If B is
A
true, what's A?
well this isn't
Not-
an or,
not-
this is an implied.
False.
Yeah, if B is true, A is false.
Right.
That's what this says.
Yes. We know
Is
A
A false?
No.
But if B is true, A is false. Is A false?
No.
So B has to be
False.
false,
Not B.
not B.
Not
Because if
B.
B is true, then A is false. But we know A is true.
Yes.
So this is tautologically implied. I'll give you another way to think about it here in a second. By 2 and 4, right?
Yeah, we're using premises.
And now we're using premises 2 and 4. So we're using premises just 2 and 4.
Not using 1.
Not in this line.
Oh yeah.
This line we did not use
That makes sense. You
this information.
Yeah.
Now here's another way that you could have seen it. What's the contrapositive of this?
It's
A implies not B. We have A using contrapositive.
Have we talked about counterpositive yet, or is that one of our tautologies?
We've already done a truth table for it. It's one of your tautologies listed out here.
Okay.
But very standard to use contrapositive. One of the most common ways of
Really
rewording
helps.
an implication. Yes, it is extremely useful. Okay, so now we got not B. Now what?
C.
Now we can conclude C. Where do we get that from?
A
5 and
implies.
6.
5 and 6. These two together. I know B or C.
Oh,
B is true or C is true, but B is false. So C has to be true. This is tautologically implied by 5 and 6. And now we are using 1, 2, and 4, right?
yeah. Okay, that makes sense.
Okay.
So we know not D.
And now you're saying we know not D.
Yeah.
Because if D is true, C is false.
We know C.
But C is true. So D has to be false. Because if D was true. Or you can think about it once again. What's the contrapositive of this? C implies not D. We know C, therefore we know not D. So either way, this is tautologically implied by 3 and what?
7.
7, thank you. 3 and 7, and now we are using premises 1, 2, 3, 4. And so what did we show? We showed if A was true, then not D was true. So 9, we showed A implies not D, given all these other premises. And so that is using conditional proof, or whatever it's called, from lines 4 to 8. And now we are only dependent upon premises 1, 2, and 3, unless it is demonstrated.
Is there ever a case where you can't get rid of the conditional premise?
You can always get rid of it. I could have gotten rid of it and said A implies B or C. And that could have been where I pulled out. I showed A being true. These and A implies this. It also implies this. It also implies this. It also implies this. This happened to be the one I cared about. So that's why I pulled out.
But there's never going to be a case where you, for whatever reason, you cannot get rid of that conditional premise.
No, you can always get rid of the conditional premise. Worst case scenario, I said I could have gotten rid of it saying A implies A. If I know A is true, I know A is true. Pretty worthless, but way you can always back out. Right? So A implies A, it's just a tautology. In fact, it's just a way of reworking this.
Yeah.
Okay, so those were some examples. Now let's go over all these rules of logic now that we've re-warmed up with everything we did last week. I don't know, we can erase this in case I want to scribble here. Okay, so every single one of these things that we have listed out here, we could construct, oh wait, first I had an example here. A note of warning. Just because we show some implication is true in a particular case does not mean it's always true. So that was one more note of warning here for how you can get tricked into thinking a rule is a valid rule of logic. So this says the sun is shining or the sky is blue. So we got sun is shining or the sky is blue. The sun is shining. Therefore, the sky is blue. Notice, is it true that the sun is shining or the sky is blue?
Yeah.
And let's assume that we are here during the day. Would it be true that the sun is shining?
No.
And is it true that the sky is blue?
Yeah.
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 But these being true has nothing to do with that being true.
Right.
So it's not enough to just find some interpretation that makes it true. You need to make sure it's true under every single interpretation.
Yeah.
So that was a gotcha that the author wanted to point out. Okay, so now all our common rules, we can prove any of these that you want. I'm just going to try and make them connect with your intuition. Because as a general rule, we don't keep one of these tables and say, can I use this one? Can I use that one? Instead, you just kind of internalize it and you just see the connections that you're doing to prove.
Are those all of them?
No, there's no such thing as all of them. These are common ones. These are ones special enough that they all have names.
Really?
Yes.
Like contrapositive, I see there. All
Yes.
of them have a name like that. Like
They all have a name.
Wow.
So all these have a name. You can go find out what the names are. Those, I think a lot of the names just come from monks in their monasteries doing logic, naming all their different rules that they could possibly come up with. You'll notice that all of these are taking two premises together to get some conclusion for the most part. All those, you can see how that's just a syllogism. So that's good old Aristotle pouring through.
Yeah. Yeah.
Anyways,
Good old what?
Aristotle pouring
And
through.
what was the word we used before that?
Syllogism. Syllogism is when you have two premises which together imply a conclusion.
Yeah.
That's a syllogism. It's like one of the simplest forms of argument there is. And that's what Aristotle, using his categorical sentences, he categorized all the possible syllogisms you can make using those.
Yeah.
Okay, so let's try and make sure all these connect with our intuition. If I know P is true, and I know P implies Q, then I know Q is true. This says if P is true, then Q is true. This says P is true. So if I know P, and I know P implies Q, then I must know Q.
Because true implies true.
Well, because if you built the truth table for it, it'd be a tautology, but I just want to connect with your intuition.
So you're trying to make it connect with our intuition. That's why you're saying if I know P is true, then I know whatever else. But when we did the truth tables, you said if P is true or P is false, then we have to make sure the truth
Wonderful.
table is always true.
So you're going to notice that as I make these connect to your intuition, I'm going to show you that when the antecedent is true, the conclusion is true. Why don't I bother talking to you about when the antecedent is false?
Because we know that that's
Because we already know the implication is true, so we don't even bother having discussion about it.
Oh, okay.
That makes sense? All we need to make sure is that when the antecedent is true, the conclusion is still true. Because when the antecedent is false, the whole thing we already know holds.
Oh.
Right? And that's the same thing you do with your algebra. When you're trying to prove something's a tautology, you just show that if the premise is true, then the conclusion is true.
Mm-hmm.
And I never say, what about when x doesn't equal 2?
Well, right.
And you say it doesn't matter.
Yeah.
So, good question. That's why we only care about when the antecedent is true. Okay, next one. if I know P implies Q, and I know Q is false, so this says if P is true, then Q is true, but Q is false, then P must be false. Because if P was true, then Q would be true, but Q is false.
So it has to be vacuously true.
What? No. This says Q is false.
Mm-hmm.
So if Q is false, and it's true that P implies Q,
Where P has to be false.
then P has to be false.
Because the statement.
Oh, now I see why you said that.
Yeah.
I was looking at this implication when you said vacuously true. But, okay. But just make that connection with your intuition.
Yeah, okay.
If I know P implies Q is true, and I know Q is false, then P has to be false. If you know that when there's fire, there's oxygen, and you know that there's no oxygen, you for sure know
There's no fire.
there's no fire.
Yeah, okay. I see it.
All right.
But that almost feels somewhat like an alpha implies beta, but beta doesn't necessarily imply alpha to me.
Like a
Yeah, I don't.
converse.
Yeah, it almost feels like what you're saying is, I know that beta implies alpha, but now I'm going to give you some information about.
Beta.
Yeah, I know that alpha implies beta, but I'm going to tell you something about beta, and I want you to tell me something about alpha, which feels like you're
Cheating.
breaking the rules.
Let me write this another way. This is not Q, if you're comfortable with this. And not Q implies not P, right? It's contrapositive.
Mm-hmm. But that makes sense, not P. Right?
Right?
So not Q. And
So if you're comfortable with P implies Q, is the same thing as not Q implies not P, if that helps to connect with your intuition,
That makes sense.
that's what it's saying.
Gotcha. Okay.
But I also just want to connect with just your regular language.
Mm-hmm.
Like if I were to tell you, if there's fire, then there's oxygen, and there's no oxygen, then you instantly say, oh, there's no fire.
right.
Okay. Yeah.
And that's a valid conclusion to come to.
Right.
And if it's a valid conclusion to come to, it must be backed by some rule of logic. There's a rule of logic, or you can write out a truth table for it. So, and feel free to say, I want to see a truth table on any of these, and that's fine, we can throw it up real quick. Okay, next one. If I know P is true or Q is true, and I know P is false, then I know
Q is true.
Q is true. If I know you ordered the soup or the salad, and I know you didn't get the soup, I know you got
So,
the salad.
Right.
All right, if I know P and Q is true, I know Q is true.
and you know.
If I know you ran a marathon and you're a millionaire, I know you're a millionaire.
And you know you ran a marathon too.
Yeah, but this for sure is true.
Okay.
So you can, it's basically saying we can break up conjunctions
Isn't that?
and deal with it piecewise.
If you know P and Q are true.
Then you know P is true.
Yeah.
And you know Q is true. All right, next one. If I know P implies Q, and I know Q implies R, then I know
P implies R.
P implies R. That's like a transitive property.
How do we know? How do
Yeah, that one is like, it feels like we're making a leap. It's intuitive, but
What is the truth table for that?
You're gonna make me do it with 8.
Yeah.
Start making some long columns. All right. Let's see. We're going to do, what are they? P, Q, and R?
PQR.
P, Q, R. Sugar. We're gonna need more space on that one. How much of this do we dare bite off in one go? Which one was I doing? This?
Yeah.
So tell me this one, then this one, then this one.
Yeah.
So what's the first one?
P implies Q. Q implies R.
Okay.
And then P implies R.
Sorry. Then we got and these two together.
Yep.
So
I don't even think you have to write the last couple. Like once you do them, I think you can see it. Yeah.
and then finally the whole thing. Okay. So we can have true, 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 false, true, false, true, true, false, 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 true, true, false.
Oh,
Sorry.
you're good.
False, true, false, 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 true, false, false, false. You give me 3 atomic sentences, has to be one of those 8 cases. Either you gave me 3 sentences that were all true, or the first one was false, the second one was true, and the third one was true, or whatever. There's everything. Okay, writing it out. This is P implies Q.
It's true.
So, true,
True.
true,
False.
false,
False.
false, true, 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 true. Right?
Mm-hmm.
Now we get Q implies R.
It's true.
True.
So we got true,
False.
false,
True.
True. True.
Wait, no, go back, that one.
No, it's true.
False. True. They're true.
I think you.
Oh, never mind, sorry.
got mixed up on your
because you're
columns.
pointing at the, yeah.
Yep, I'm just pointing at the row.
That's false, by the way. That second one at the bottom, false is
No,
not.
it's back.
No, it's back to the
False applies anything.
Oh, my bad. I read it wrong. Yeah, yeah.
There's only 2 falses that are going to show up, so I know once they're there, the rest are true.
Yeah.
Okay. P implies R. These two.
It's true.
True.
That's false.
False.
That's
True.
true.
False. True. 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 True.
Good? All right, anding these two together.
That's true.
True.
That's false.
False.
That's false.
False. Or true. That's true.
False.
We're
False.
anding them.
Anding. I'm sorry.
Yeah, that's false.
False.
That's true.
True.
That's false.
False.
That's true. That's true.
True.
Alright.
Okay, now finally, we're doing and implies this. This and this implies this. So our implication is going right to left. Don't get confused.
Gotcha.
So I'm going to point here, but we're doing this implies this. So true implies true is.
True.
False implies false is.
True.
False implies true is.
True.
False implies false is.
True.
True implies true. False implies true. True implies true. True implies true. Okay. Da 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 da.
That's really cool.
Because of that and.
Wherever it makes it connect, you'll stare at it until it clicks, and then you'll forget in 2 weeks. And repeat.
It's a transitive property, though.
Yeah.
You can think about it like that. Transitive property applies to relations. Not really a relation, but I'm okay with you saying it. Okay, so we got that one, right? Is it connecting with our intuition?
Yeah.
Yes.
Okay.
Yeah.
Now, if I know P implies Q and not Q, a contradiction, then I know not P. Now, I don't know if I'm supposed to have my not here or my not here, and I'm not sure how he does it.
Not
They're
P.
logically equivalent.
P
That's
implies a
tautology.
contradiction.
Wait.
He
Q-
probably puts the not here. Not P, if not having P implies a contradiction, then P must be true.
That's what we use when you.
If
do-
P being false is impossible,
Perfect.
then P is true.
Yeah,
So that's the rule we use when you do perfect computation.
It's a piece of it.
Piece of it? Okay.
Because you'll see why here in a second, but it's kind of like CP here where we introduce a premise and we get rid of it. The reason that we could do a truth table for this is because our set of premises could be infinite or some non-finite number, and so or some arbitrary number, and so you can't do a truth table for an arbitrary number. So that thinking backs it, and that's what we use as our intuition for it. But it doesn't prove proof by contradiction.
Can
That
you
makes
prove perfect computation?
Not really.
I don't know.
Because it's like you're asking for a derivation of a rule of derivation. So in that sense, no. Can you make it appeal to your intuition and come up with an argument that you say, okay, yeah, that makes sense? Yes. But will it actually be a derivation? If that's what you mean by proof, then the answer is no. In like way, I tried to come up with the truth table to make this make sense to you, where I use fancy P to represent my conjunction of all premises. But that's not the same thing.
So we have to introduce perfect computation as a rule.
So the author, he proves it using this thinking together with this, but he doesn't prove it with a derivation. He gives you an explanation as to why this is okay. But it's not on the same level as these rules are here. Because there's some purists out there who don't accept it as a rule. And they do all their derivations without using proof by contradiction. As far as we can tell, it doesn't change anything, and it just makes your life much, much harder. But there are some almost French-like mathematicians who refuse to use the rule.
So
It's
we-
beneath them.
So we do not.
French like.
Seem like the right adjective.
So
Something
is
snooty.
Is it accepted as a rule or not?
Yes.
99.9%, 100% of sane mathematicians, yes.
Okay.
It's not stops.
Gotcha.
All right. I lost what we were doing. We were on this one. Okay. Were you okay with this? If P being false implies something that's impossible, then P must be true.
And that works if you move the not, right? So if P implies.
Yeah, it could have been
Okay.
that with the not there. I'm guessing the author puts the not there. But the point is, if this being one way implies a contradiction, it must be the other way.
Yeah. Which makes sense. Okay.
Good with this one?
Yeah, but that's why students don't understand proofs, is we don't have that conversation. We just throw them into a proof by contradiction without any discussion on it.
What we do to kids is completely asinine. Going back, there's this curriculum that we call the 7 liberal arts. That stood for 2,000 years. And we just throw it out the window like it's nothing and come up with our own curriculums, changing left and right, and we don't get the foundations anymore. Logic was one of your 3 most foundational courses in academia. And we just throw it out the window around the year 1900. No, we don't need that anymore. Kids kind of just get it. And you put them in a geometry class where they have to use logic. That's as asinine as, we're going to go take a writing class, but you've never done grammar before. How the heck are you supposed to know how to write about something when you don't know how the rules of writing in general? It's crazy. And so geometry books have to put logic at the start, even though logic is not geometry. They're very different.
Yeah.
That's like calling calculus physics. No, you use calculus and physics, they're still very different. You use logic and geometry, they're still very different. So it's a nightmare, which is one of the reasons I teach logic. It's nuts. Poor kids. And it's one of the reasons geometry is such a difficult course for kids. Okay, we did that. Next one. I think this one's pretty intuitive. If I know P is true, then I know P or Q is true. If I know you ordered the soup, then I know you ordered the soup or the salad. Okay,
Could have ordered both.
could have ordered both. Okay, now I told you all our rules of logic are implications. Now we're getting to equivalences. Did I lie to you?
No. There's
No,
double
because
side.
this is stating 2 implications in one go. It's saying, if you know this, then you know this, and if you know this, then you know this. So that symbol is often referred to as a biconditional. It's 2 conditions.
That is saying the same thing as P implies that and that implies P.
Yeah.
Right, this says P implies not Q, P implies not P, and not P implies P. Both of those are true.
Gotcha.
So if you have this in your derivation, it's valid to replace with this. And if you have this in your derivation, it's valid to replace with this.
And when
Or
you're
comes to that
proving-
conclusion.
When you're proving an equivalence, you have to prove both implications.
Well, when you're proving it with the truth table, it's the same thing. We're saying this is a tautology. Build out the truth table, better all be true.
Because it has its own rules. The if.
When we build out a truth table for this, do we show both implications on the truth table?
That's what this is checking. This is saying this implies this and this implies this. So if your truth table is always true, then it's always true that this implies this and this implies this. So you're checking 2 implications in one go. Notice if we tried to do that with this, we wouldn't get it. This implies this is true. If we tried to do the other way, that one doesn't work.
Because the only time the equivalence symbol is true is if the 2 sides are both true.
Right, so I'm just wondering.
No, they could both be false.
Or both be false, if they're both the same.
They have the same value. So every time this is true, and every time this is false, this is false. And so true implies true is true, false implies false is true, true implies true is true, false implies true, or false implies false is true. Okay. I think that was pretty obvious, huh?
Yeah.
most straightforward one. All right. Here's your contrapositive. P implies Q is the same thing as not Q implies not P. If there's fire, then there's oxygen. It says the same thing as if there's not oxygen, there's not fire. Next one. This one we spent a lot of time with on the first class. It's how you distribute a not over an or. It turns it into an and.
Right.
Yes.
So not P or Q is the same thing as not P and not Q.
Is that De Morgan's law? Is that what's
Yes, that's called De Morgan's. So not P or Q says not P and not Q. If you said, I got the soup or the salad, and I said, you're a liar, I'm saying you didn't get the soup and you didn't get the salad. Next one.
But you just negated something.
Right.
Right.
Oh, the not-
I'm saying
the
the
not.
negation of this is that.
Gotcha.
Yeah.
Okay.
So similar thing here. If you said, I got the soup and the salad, and I said, you liar, what am I saying? I'm saying either you didn't get the soup or you didn't get the salad. So not P and Q is the same thing as not P or not Q. And then these ones are obvious. P and Q is the same thing as Q and P. Doesn't matter what order you and in. Or in other words, it's, what's that property called?
Symmetric. No.
That has to do with relations. This is an operation.
What?
Commutativity.
Oh.
And is commutative. And this one says or is commutative. P or Q is the same thing as Q or P. Now this says P and Q and R is the same thing as P and Q and R. What's that one called?
Associativity.
Associativity, there you go. And same thing with or.
Okay.
In other words, when you're doing your grammar, you're writing out a list of this and this and this. Doesn't matter where you put the comma. Similarly with the or. If it's this or this or this, it doesn't matter where you put the comma. If you want or those first and then or that, or if you want to or that and then or those first and then or that. Although I don't know how you write that in grammar. I guess you just put it P or Q or R. Yeah, that could work. Okay. Hopefully those ones are as straightforward as I think, right?
Yeah. Escape.
Okay. So now, very weird one, and very useful one. P implies Q is the same thing as not P or Q. I want to do that truth table for that one for sure. So that's what we did over here. Here's the truth table. Here's how it's always true. Because that one is not very intuitive. And that is not one that just clicks in my brain. It's just one that I remember. P implies Q is the same thing as not P or Q.
Why is that useful?
Imagine you want to negate an implication. It's way easier to negate a disjunction. Distribute the not and turn your or into an and. Thinking about how you negate an implication is kind of annoying.
How do you do that?
It's the same way. So I say, if I'm wearing shoes, then I'm wearing socks. And you call me a liar. What are you saying?
You're saying that.
You're saying that I'm wearing shoes and I'm not wearing socks. That's what you're saying.
Oh,
Negate this.
exactly what you get. Okay.
But that one you kind of have to think through. How would that be false? This one you just carry out the operation without even thinking.
Gotcha. Okay.
And if it were a more convoluted one, it can be hard to think about. Anyways, so P implies Q is the same thing as not P or Q. This is what we just did. Negating an implication is the same thing as P and not Q.
Yep.
That's why I just barely wrote out, so glad we did that.
Makes sense.
Next one. P and Q implies R is the same thing. So let me say this. If I know, going to read the sentence here. This is if, then. If I know P and Q are true, then I know R is true. Says the same thing as if I know P is true, then if Q is true, R must be true. If P and Q are true, R is true. If P is true, then if Q is also true, R is true. If P and Q are true, R is true. If P is true, then if Q is also true, R is true. See it?
Working on.
This is what we're using with this is the intuition behind what rule CP is doing here. It's saying if your premises and Q implies R, then your premises implies Q implies R.
Oh.
But when I did it, the truth table for that, rather than putting a P here, I did the fancy P, which represents the conjunction of all our premises.
Gotcha.
But that is what I did. And then finally, my one lie to you. I told you every rule of logic is an implication. Technically, these can be restated as implications, but we never do it that way. So here's our two exceptions. Rule of logic, P or not P. It's called the law of excluded middle. It's always the case that P is true or not P is true.
Yep.
One of those always has to be true.
Yep.
You either have P or you have not P.
Yep.
If I say I have P and you say you're a liar, you're saying I don't have P. Because you're always asserting one of those. And similarly, this is called the law of contradiction. It is not the case that you have P and not P.
Right.
Which
Or
is
in other
the
words,
same thing as-
P and not P is always false, so not P and not P is always true.
That's saying the same thing as not P or P.
Right.
That was the law of what?
This one is the law of contradiction.
Isn't that the same as the law of excluded middle? When you distribute the negation.
You can take this, distribute the negation, and get something that's equivalent to that.
So why do you even bother stating it as its own rule or its own law?
So our people who reject our rule, our reductio ad absurdum, they also reject this.
But they keep the law. of
They do not think that you can just say either P or not P. Has to be true. And you always have to prove it's true. Notice that these are very strange. So anytime we use these other rules, we had some starting information and we applied the rule to get some new information. This is not starting with some information. You can just insert that and start working away with it. They don't like that. They think you should always have to construct your way to what it is you're doing.
So do they reject both of those?
No, they're okay with this, that you can't call both these true.
Okay, but is that not the exact same as?
It's almost like they're leaving open that you could have some third possibility, true or false or square. They're okay with the fact that you can never have both P and not P are true.
Well,
They're okay with that.
you have to-
But they're not okay with it has to be true.
Okay, but is that not
That's
the
not a
exact
statement.
same? Is that not the exact same?
No,
Are those
you're
not saying the
you're
exact same
already, the reason that it's not is because we already have built into our intuition, because we're seeing, that all these propositions are either true or not false. And if it's true, then it's not false. And if it's not false, then it's true. And that's the thinking that we're using. They reject that thinking. They don't think just because you show that something's not true, or just because you show something's not false, then you get to accept it as true.
But when we distribute that negation, is it not the exact same sentence?
Yes.
It is.
Because we have built into our notion that we're always accepting something as true
Or false.
or false.
And it's not true. and
They're
false.
not. They look like they're logically equivalent statements.
They are logically equivalent because we're already really using this rule
Right.
in our thinking.
So there are laws.
You are already using in your thinking when you're trying to come up with truth tables for these that every statement is either true or false. That it's always P or not P. It's not worth getting caught up on the subtlety. They reject this, they still accept this.
Is that why we make the? Is that why we distinguish between the two?
It's a reason for it.
I see.
But we also just use that by itself, and we use that by itself. So it's just a matter of what's useful to grab.
But they are saying the same thing.
You can see how they're saying the same thing. You're saying that distribute the not over that gives you that,
Yes.
using other rules of logic that we have.
Yeah.
That's true.
Okay.
So there are two different ways of writing the same thing, given our rules of logic, that we've already accepted as true.
How do they? What? Okay. That's so weird.
But we use them a bit differently, because we will sometimes use this, and we'll be going along and we'll say, well, either this premise, we'll introduce something, going along, and we'll have like, as a line in our derivation, 6, just out of the blue, we'll say, well, I know either P or not P, and I'll start working with it from there. So I'll just shove that in there out of nowhere, and it's not implied by any other line. I just shove it there. And so this is going to be using rule T, but it's not tautologically implied by previous lines in the proof. It's tautologically implied by nothing in the proof. We just shove it in there and go on our merry way.
But it's one of our tautologies.
And so, what premises is that dependent upon? Those ones.
Is that wrong?
No, but you see how it's a bit strange. And so that's how we're going to rip it out and use it when we need to use it a lot of the time. So my point is it's useful to have it expressed that way. Rather than we're not really going to pull this out and use it that way a lot of the times. Instead, we're going to say we know that contradictions are always false. And that's how we think about that rule. And so that rule is useful in determining a contradiction. This rule is useful when we don't know what to do and we just need something to start with and get going. Okay. And with that, we did all that. So next is consistent. All right, got that. And we still have our scratch area. We basically have all the rules. I don't know if I'll need them, but good to know. We can see all that. Okay. So, next we're going to talk about this notion of a set of premises being consistent versus a set of premises being inconsistent. Intuitively, what does it mean for a set of premises to be consistent? Imagine you're a parent, you got two kids, Jack and Jill, and Jack and Jill come to you crying, and Jack says, Jill hit me first, and Jill says, Jack hit me first. What do you know? At least one of them is lying. Right? Those premises can't both be true. Those premises are inconsistent.
Can they both be false?
Well, maybe in that particular case they can, but in general, when premises are inconsistent, it's because they can't both be true. You got a child, you say, where were you last night? They said, oh, I was at Jack's house. And then you say, where were you last night? And they said, oh, I was at Jill's house. And they forgot the story they already told you. Now you know one of their stories has to be false. Both their stories could be false. And they could have been at Bob's house. But they can't both be true.
Gotcha.
So, consistent premises are premises that can altogether be true. It is not guaranteed that one of your premises is false. Inconsistent is you're guaranteed at least one is false.
So you're guaranteed.
Consistent means they can all be true.
Okay. Yeah, all right.
Okay, that's high level. Now let's say it again. Consistent. A set of premises is consistent provided that they can altogether be true. Otherwise, they're inconsistent. If it's impossible for all of them to be true.
Is that a definition?
Yes, consistent versus inconsistent premises. Now, in logic, what do we say? We say if the premises are true, then the conclusion is true. That's what we're always arguing in logic. If this is true, then that is true. And so, it makes zero sense to try and apply logic to inconsistent premises. Because it's impossible for all the premises to be true. It's a waste of our time to work with it. So we're very interested in whether or not premises are consistent.
What happens if we try doing that?
What happens if premises are inconsistent?
Yeah.
Then I can prove anything. Because if they're inconsistent, that means they somehow contradict each other. I can use that contradiction, which is always false, and false implies any statement I want, S, is true. And now I can prove S, regardless of what it is. I can prove S is true, and I can prove not S is true. So I can prove S is false. I can prove everything. If you allow 1 to equal 0, that is inconsistent with the axioms of arithmetic. Because one of our axioms of arithmetic is 1 is not equal to 0. If you also add and 1 is equal to 0, inconsistent. I can now prove anything. Because false implies anything is true. Inconsistent premises will allow me to get contradiction. Contradiction implies anything is always true, vacuously. So the whole system becomes useless. Because now everything's true and everything's false. And so logic has nothing to say. So in logic, we say if the premises are true, then the conclusion is true. And so we're very interested in whether or not our premises are consistent. Because if they're inconsistent, then it's impossible for them to all together to be true. And it makes no sense to then try and apply rules of logic to inconsistent premises. Okay. Now note, going back to criterion 1 from last time. Criterion 1 says we can only derive true conclusions from true premises. Right? If our premises are true, all our conclusions have to be true.
No.
If I come to a false conclusion, then, what do I know?
One of your premises is false.
One of my premises must be false. Criterion 2 says, we can only derive true conclusions from true premises. So if I derive a false conclusion using the rules of logic correctly, then I must have somewhere had a false premise. This is kind of what we do with reductio ad absurdum. We say adding this new premise makes our system inconsistent. So the negation of it is what must be true, and we go in our merry way.
I see.
Okay, so in general, how do we show inconsistent premises? There's two ways we can do it. One is a truth table. We just take the conjunction of all our premises, and if it's always false, then our premises cannot altogether be true. So we're at the truth table, and if your truth table says false, in that column says false, 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 all the way down, however many there are, then your premises cannot altogether be true.
Well, if it doesn't say true, 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 our premises cannot altogether be true.
No, it just has to say true once. Then your premises can altogether be true. Is it possible, quick example, is it possible to have alpha and beta as true premises?
Yes.
So we could have true, 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 false, false, true, false, false. I tell you, I went to the store and I gassed the car. Is it possible are those premises consistent?
Yeah.
Yes, if they're consistent, then that means when we conjoin them, when we do the conjunction of them, there has to be at least one true. And in the end case, there's only one true.
So if there's ever one true, then the premises are consistent.
Right, it is possible for all your premises to be true.
It is possible.
If it's possible for all your premises to be true, it's consistent. A set of premises is consistent provided that they can altogether be true.
Not that they are all together true. Like,
When you take the conjunction of them all, that can be true. There's a way to satisfy it. There is some row in your truth table that satisfies it. On the other hand, if I told you alpha and not alpha, you cannot have both of those premises be true. They're inconsistent. And so if we did the truth table for this, we have true, true, false, false. Here, not alpha would be false, false, true, true. Add them together and we get all false. And so these cannot be two of your premises. Something's got to give.
Gotcha. So just because it's consistent doesn't mean it's true.
Just because it's consistent doesn't mean it's true. Consistent means it could be true.
Okay.
Okay, so showing inconsistent premises, one way to do it is with the truth table. We take the conjunction of all the premises and see that it's always false no matter what. That column, always false. Second way we can do it is we can derive a contradiction.
Yeah. Yeah.
That's using the thinking we have up there. Criterion 1 says we can only derive true conclusions from true premises. If from my premises I can derive a false conclusion, a contradiction, then one of my premises had to be false.
And that's how we do proof by contradiction.
And that's how we do proof by contradiction. We say, what if I add P as a premise? And we get, well, then that leads to alpha and not alpha. And so I say, okay, then not P must have been what was the case. What if P was the case? That leads to some impossible picture. Oh, so not P was the case. And we go on our merry way. And you see how we're using rule of excluded middle there, which they hate. Okay. So both these cases make sense for how we show a set of premises is inconsistent. Yeah. Either truth table, and it's all false, or we're somehow able to derive a contradiction. Okay. So, do an example. I tell you, if I'm wearing shoes, then I'm wearing socks. And I tell you, I am wearing socks, I'm wearing shoes and not socks. Are those premises consistent?
No.
And the answer is no. We'll do the truth table really quick. You guys already see it, so maybe truth table is a waste of time, but I'll scribble it out really quick. So here's all the possible combinations. True implies true is true, false, true, true. Alpha and not beta. So true and false is false. True and true is true. False and false is false. And false and true is false. Now finally, we're conjoining these two together. So true and false is false, 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 false. And so it's impossible for both those premises to be true.
Makes sense.
Consistent, not inconsistent.
Yeah, so if you can show, this is how we show something is inconsistent.
Yeah.
How do you show it's consistent? Well, you show that it's not inconsistent. Or in other words, if a true comes up, then they're consistent. Or if we can find some interpretation that satisfies all the premises and all the premises, just that,
Yeah.
then they're consistent. Okay. I think we are ready now for our next example. Or introducing our last rule and then doing our last examples. Ooh. Run out of space. Oh, come off it. Look on the camera really quick and tell me when I'm good. Is this good?
Yeah, you're fine.
Alright. Don't go past there. Although my projector goes past there. I don't know if we'll even get to homework problems. Worry about later. Okay. Our next rule. So this is now another rule of derivation. So far we have our 3 rules over there, P, T, and CP. Now we're introducing rule RAA. Why is it called RAA?
Reduction ad absurdum.
Reductio ad absurdum. Or reducing to an absurdity. That's what the Latins would do. They would show some position, reduces to an absurdity, therefore reject the position. How does this rule work? If a contradiction can be derived from, what does fancy P stand for?
The conjunction of all your premises.
The conjunction of all your premises. So if my premises are P1, P2, and P3, fancy P is shorthand for P1 and it together with P2 and it together with P3.
They can be for an infinite set of premises.
Well, I don't know how to work with an infinite set of premises, but some indefinite number.
Wow.
We don't know what the number is, which is why we can't do truth tables with fancy P. I'm going to do a truth table with fancy P, but I'm cheating. Right? Because when I take the conjunction of all your premises, however many you have, when I add them all together, it's either going to be true or it's going to be false.
So why is it cheating to do a truth table?
Because how do I make explicit what I just explained to you? I'm just making it appeal to your intuition.
What?
We can't do it with the truth table because I would need to validate that with the truth table.
Oh.
You accept that when I and 3 things together, that's true or false. What if you and together 4 things?
Is there no way of deriving that any number of things added together is true or false?
You're wanting to use proof by induction, which is way higher level than logic.
Yeah.
And the basic logic that we're using for truth tables.
Okay.
So no, if you show it with the truth table, you have to show it with the truth table.
That's fine.
So it's a little bit higher level.
Okay.
You get what I'm saying, and so you're okay with this as a rule. But this isn't a rule like our rules of logic are rules. These we can validate directly with the truth table.
So
Here, we're saying this is a valid rule of derivation, and you see it. And you see that obviously it doesn't matter how many I and together, it's going to be true or false. And that's a connection you're able to make. Because you're a human.
right.
Alright, so that's what fancy P stands for, is just a conjunction of all our premises. So a conjunction of all our premises has to be true or false. Maybe red will show nice. So we can have all our premises are true or false. Now what are we showing? We're showing if a contradiction can be derived from all your premises and some new statement you're considering, not S,
Okay.
then S can be derived from your premises alone. So if your premises together with not S implies a contradiction, then your premises imply S. Maybe say it again as we fill this out. But anyway, so we're looking at the conjunction of all your premises, and they're either true or false. And then S here is either true or false itself.
Right. Yeah.
So we can have true. Here's all the possible combinations, right?
Yeah.
Okay, so over here we're going to do P and not S.
Okay.
So true and false is,
False.
true and true is,
True.
false and false is,
False.
true and false, or false and true is. Okay, and now over here, what are we saying? We're saying this implies false. Implies a contradiction, a statement that is for sure all false. So that's not F as in standing for something. That's F as in false, something that's for sure false. So maybe I should have said implies A and not A. Something that's always false for sure. Okay, so false implies false is.
True.
True implies false is.
False.
False implies false is.
True.
And false implies false is.
True.
All right, now let's look at P implies S. True implies true is.
True.
True implies false is.
False.
False implies true is.
True.
And false implies false is.
True.
So they're logically equivalent. And so if I know that P and not S implies a contradiction, then I know P implies S.
Alright. Makes sense. Is there a word for a statement that's always false?
That's what a contradiction is.
A statement's always okay.
A contradiction is, well, I should be careful. A contradiction is when you have specifically A and not A.
That's what inconsistent.
When you're stating something and its negation.
Okay.
Inconsistent premises means that all your premises, when you and them all together, can never be true.
Right.
So different things.
Okay.
What's something that's always false?
A contradiction.
A contradiction is an example of something that's always false. But a contradiction specifically says A and not A.
But we have a word for something that's always true.
A tautology.
I wonder if we had a word for something that's always false.
If something is always false, is it somehow encoding the contradiction? I don't know. It could be the case. And so you could be okay saying if something's always false, it's a contradiction.
Or contradiction.
It would have to be, right? If it's always false, somehow it has to be encoding that something's both true and false. That's the only way it can always be false.
So, a contradiction is a statement that's always false.
I think that works.
Okay.
And if it's contradiction, somehow it's encoding A and not A. Not positive.
Alright.
Okay, so that's the rule. The rule makes sense?
Perfect. Yep.
So we're going to reprove this example. It's the same thing we proved right here.
Okay.
But this time I'm going to prove it by way of contradiction.
Okay.
So, just rewriting out, here were our premises. So one, we had A implies B or C. Rule P, only dependent upon itself. Next we have B implies not A. Rule P, only dependent upon itself. Next we have
D implies not C.
implies not C.
D implies not C.
We're trying to prove that A implies not D.
We're trying to prove A implies not D. Now, let's do a couple steps of thinking. A implies not D is the same thing as what? If we write it as an or. It's the same thing as not this or this. So that's the same thing as not A or not D.
Not A or D.
Well, I don't quite see that.
That would be A implies D. If I had A implies D, then that says the same thing as not A or D, right?
Oh, yeah, okay.
So it's not the first thing or the second thing. Not the first thing or the second thing.
Okay.
Make sense?
Yep.
Now, we want to assume by way of contradiction the negation of this, which is the negation of this. Or here's a better way I could have said it. What is the negation of P implies Q? It's P and not Q. So maybe that would have been a better way than using that middle step. So, what's the negation of P implies Q?
It's B and
It's not, or it's P and not Q.
Yeah.
See it?
And then the negation.
So
of
this
that.
is the negation of this.
Why are we negating this again? What's the point?
You're negating it and negating it.
Just gonna try
We're
to
gonna do
different
P
ways.
and not S, and show that implies a contradiction. Therefore, P implies S.
So we're gonna assume A and not D? Or we're gonna assume A and D?
We're gonna assume A and D, and get a contradiction, and therefore we know not A and D. And not A and D is the same thing as
Not A
distribute
or
your
not
not A or not D, which is the same thing as
D. A implies not D.
A implies not D.
Alright, I see it.
Okay, so I'm introducing now. This is, if we were writing a proof, this would be where I say assume by way of contradiction.
Yes, this is your,
That-
your conditional.
A and D is a premise, but it's a premise I promise I'm going to get rid of when it's all said and done.
Conditional premise, right?
Okay, now 5. If I know A and D, what do I know?
You know
You know, A and D.
that D.
Well, pick one. Which one should I work with first, A or D?
I would pick one.
If
I-
A is true, then
So A
B
implies-
Let's really quick just pick A first. So then I know A is true. This is tautologically implied by line 4, and we are only dependent upon 4 for our validity.
Uh-huh.
Okay, so now we got A. What does A give us that's new?
B or C
and
is true.
B or C. Yeah.
So it gives me B or C. So I can conclude B or C. This is tautologically implied by 1 and 5. Am I seeing that right?
Yeah.
And we're using premises 1 and 4.
Okay, we know D is true, so we know that not C.
Well, then
We know
So
D.
let's really quick add D here.
Yeah.
Is line 7. This is tautologically implied by
4.
just 4. And it's only dependent upon 4 for its validity. Okay. Now you're saying combine D. You're thinking these two?
Yeah.
Okay.
7 and 3.
So not C.
So
Not C.
8 we get not C. This is tautologically implied by 3 and 7.
Yep.
And so 3 we had only 3. 7 we had 4. So that's 3 and 4. Am I right?
This is correct.
Okay. Now, what were you wanting to combine?
Now we have B.
So now you can include B. So 9, now we get B. That is coming from
Yeah.
6 and 8.
Uh-huh.
Tautologically implied by 6 and 8. By the way, there isn't one right contradiction. You might all be seeing, wait, aren't we going to go for A and not A, or B and not B, or C and not C? There's a lot of different ways you could do it. So there isn't the right way. So we're taking 6 and 8 together to get B. And so we're using everything but 2, right?
Yeah. 1, 3, 4.
1, 3, and 4. Okay,
We know B implies not A, so not A.
so now using 2, we get not A. And that was tautologically implied by
2.
2 and 9. And now we're using 1, 2, 3, 4. Right? And now what do we write finally?
What do we write?
Not going to give it away.
Contradiction. Do we do the?
You have your contradiction.
What's your contradiction?
A and not A.
A and not A, so write that out. So now we have A and not A. This was
That's
tautologically
like
implied.
5 and 10.
And, yeah.
5 and 10. And now that's where we would put your back and forth arrow if we were doing a standard proof. But here we come 12, and so now we just write not A and D. And that was using rule R, A, from line 4 to 11. From 4 to 11, and now we are no longer dependent upon 4 as a premise.
So 1, 2, 3.
So 1, 2, 3. And now, not A and D is the same thing as A implies not D, distributing the not through and doing the or. So 13, this is the same thing as A implies not D, and that is tautologically implied by line 12. and we are dependent upon 1, 2, and 3. Good with that?
Yeah.
So, redoing the problem with a reductio ad absurdum proof. Okay. I think I want to start with another one of these next time. So I'm going to leave example 5 for next time because that will be another reductio ad absurdum proof. So I'll re-go over the 4 rules next time, do another example of a reductio ad absurdum, and then we'll continue on our merry way.
Thank you.
Yep.
Yeah, thank you.
All right. Turn off the camera.